Welcome to day 11. Your homework for today says finished packet started in class. Now I put that packet in your notes packet, so it's the last like 3 or 4 pages. I think it might be 4 pages in the notes packet. They're AP style problems. They're labeled questions 1, 2, and 3. We're going to do number 3 in the video, and then 1 and 2 will be left for you to do on your own. So here are your homework answers. You can pause it and check your answers. And then I'm going to talk through each and every one of these because sometimes these can be a bit challenging to see where they're coming from. So you can listen to the ones that you need help with. All right, this first one, it's a improper integral because the 0 will make it a discontinuity. So we're going to have to do limit as a approaches 0 from the right. The antiderivative is pretty basic. Fill in your 4 to get 4, and then fill in your a. So as a gets close to 0, that second part will just be 0, so it converges at 4. In number 4, we were going from 0 to 2. 1 will make the denominator 0. So when you've got a discontinuity in the middle of the interval, we've got to split it up into 2 parts. We'll do 1 from the left, 1 from the right. The antiderivative was the same for both of them. Fill in your b's, fill in your zeros. So when you get down to the line where we now want to evaluate as b is approaching -1 from the left, doing direct substitution works for both these. You just put in 1 for the b and for the a, so you end up with 3 plus 3, so we're converging at 6. Next one, we had an infinite discontinuity at 0. Since it was inside the interval, we had to split it up into 2 parts and look at 0 from the left and 0 from the right. Think of that as x to the -2 when doing your antiderivative. We get -1 over x for each of your antiderivatives. We'll fill in the b and -1 and along with the 1 and the a. In the first one, when we go 0 from the left, that means a tiny negative number. So think of it as -1 over -1 over 1,000. When you do keep, change, flip, that'll be a big positive. Similar idea with the other one, +1 over 1,000, keep, change, flip will give you a big positive. Anytime you got infinities in there, it's automatically diverges. In 13, our issue was the negative infinity for our lower bound. So write it as a limit. This is a mismatch product, so you've got to do integration by parts. U would want to be our polynomial. That's our third one in our hierarchy. So go ahead and do your integration by parts, and that takes you down to here. Sub in your 0 gives you 0 for the first term, and -1/4 for the second term, and then minus, put in parentheses, fill in your a's. Well, this part here, they each have an e to the -2a. So if you put in negative infinity to the e to the -2a part, so right here, that's going to give you e to the infinity. And you want to make sure you know what the graph of e to the x looks like. As x goes to infinity, that's getting huge. And then the parentheses part, -1/2 times a negative huge number will give you a positive huge number. -1/4 is still a positive huge number. So that's a huge times a huge. That's got to be a huge. But then it's getting subtracted. So this is like -1/4 minus infinity. Even if you had thought of it this way, okay, anytime there's infinities in there, it's automatically a divergence. All right, so we had an infinity as one of our bounds. That was our issue here, why it was improper. You had to do integration by parts. Integration by parts took you down to here. When you filled in the b approaches infinity, this will be a huge number -1, which is still a huge number. This part here, e to the negative infinity, will send you towards 0. And technically this, I think that should be a negative infinity there. But, and that should be a negative infinity there. So that leads us to L'Hopital's, because we've infinity times the 0 is a indeterminate form. So move that e to the negative b to the denominator. So you get a negative infinity over infinity. That's one of our L'Hopital's cases. Derivative of the top is -1, derivative of the bottom, e to the b. So now as the bottom gets huge, and -1 over enormous numbers just approaches 0. So therefore, this whole part was 0. This one was 0, and those were 0, so therefore it converges at 0. Problem with 28 is the 0. Make it undefined, so we're going to 0 from the right, do your antiderivative, fill in. In natural log, if you're going to 0 from the right, you want to be comfortable with what natural log looks like. So as we go towards 0 from the right, that would be a negative infinity times a -8 will be a huge positive number. So we'll just get infinity, so diverges. The issue in 29 is the 8. It'll make it undefined, so we want to do limit as b approaches 8 from the left. You got to do a u substitution. After doing your u substitution and changing your bounds, you get to this when you do your antiderivative. When we fill in, direct substitution with the 8 just gives us 0, so this is going to converge and it'll approach 6. Here, tan has an asymptote at pi over 2, so we got to change that to b approaches pi over 2 from the left. Your antiderivative tan, negative natural log cos absolute value cos theta, fill in your b and fill in your 0. Cos of 0 is 1, natural log of 1 is 0, that gives us that part. Cos, as we approach pi over 2 from the left, we are approaching 0, but think of it as tiny positives. So we're basically approaching 0 from the positive side. So now your natural log graph, as you approach 0 from the positive side, is a negative infinity, times that negative will give us a positive infinity, therefore that diverges. (36), the 2 is our issue, so we'll do limit as b approaches 2 from the left. That's an arc sine with an a value of 2. When we fill in, it'll give us arc sine of 1, which is just pi over 2. The 0 gave us arc sine of 0, which is 0, so that one does converge. In 38, you've got to do partial fractions. So factor your denominator. You eventually get -1/4 for the 2 minus x and +1/4 for the 2 plus x. Antiderivatives, you got natural logs there. So just because it's a little confusing, that minus is on the 2 right there. So that's saying 2 from the left. And then in that first integral, when we do our antiderivative, we need a negative correction. So that's why the -1/4 is now out there. So as you go to 2 from the left, both inside these absolute values are going to get close to 0. And the absolute value part makes it going 0 from the right. So we saw in a previous problem, when you go to 0 from the right for natural log, that's going to negative infinity. So you get infinity minus infinity. Anytime it's infinity involved, it diverges. 39, 1 is an issue. It's in the middle of our interval, so we got to split it into 2 parts. The antiderivative there is hopefully pretty straightforward. When you fill in for b, direct substitution works. So you end up getting -3/2 plus 3/2, so it converges to 0. And 42, we've got 2 issues. The 1 is a problem because natural log of 1 is 0, and we've got infinity. So our improper integral needs 2 parts. We're going 1 from the right, and we're going to infinity for our b. So a quick u substitution, use natural log of x, du is 1 over x, so you get 1 over u. Antiderivative would be natural log absolute value of u. Our bounds got changed to natural log of a and 1, and then 1 to natural log of b. Fill those in. And when you're doing the one from the right, this one, as natural log approaches 1 from the right, you're getting close to 0. And then natural log as it approaches 0 is negative infinity. Minus negative infinity gives you a positive infinity. Here, as natural log goes to infinity, you're heading towards infinity. Then you're doing another natural log of infinity, so that heads towards infinity. So it diverges because we got infinities. All right, so again, in the back of your notes packet, this is the first question you'll be doing on homework tonight, but this one we're going to leave for you to do. And we're going to do number 3 together in the video, and you'll have to do questions 1 and 2. So an experimental fish hatchery tests new approaches to water treatment and fish rearing. It works with the Arctic grayling, a traditionally hard to culture fish. The population of this fish in this environment is given by a logistic differential equation that's given there. T's in months, P is always greater than 0, our population, and we've got a slope field given for it. So P equals F of T, that's our solution for the differential equation, some particular solution given an initial condition. So we're going to say the fish are initially stocked with 100 Arctic graylings, and we're going to use Euler's method to show that they die off. So it's been a little while since we've done Euler's method. Euler's method, we make our table. So we do our x value, which is t in this case, our y value, which is p. Next we do our dp over dt. And then lastly, we do our dp over dt times our delta t, what we're changing by each time. So we started at t equals 0, and we'll be doing a step of 0.1 each time. So like 0.1, 0.2, 0.3, and so on. Well, our population to start was 100. And if we fill in to our dp over dt, that would give us 0.01. Fill the p in, 100 times a negative or minus 200 will give us negative 100. And then 800 minus 100 will give us 700. Well, 0.01 times negative 100. Maybe let me make this line a little further over. So 0.01 times 100 will give us negative 1, times the 700 will give us negative 700. So now we've got to do that negative 700 times our step size of 0.1, so that gives us negative 70. We apply that negative 70 to the previous y value. 100 minus 70 gives us 30. And now we'll repeat with the 0.1 and the 30. So we'll put it in our differential equation again. So we have 0.01. We're going to have 30 minus 200, so we'll have times negative 170. 800 minus 30 will give us times 770. And if we multiply that out, we should get negative 1,309. So if we do that times our 0.1, it'll give us negative 130.9. But if we apply that to the previous population, we get negative 100.9. Well, a negative population means there's none left. Okay, so what this shows is the population will die off between 0.1 and 0.2 months. So it is kind of hard to see here, which is why I want to do this one together. But here where it's leveling off, that's 800, and here where that's leveling off, that's 200. In between there, they're all positive slopes. Above the 800 is all negative slopes, and below the 200 is negative slopes. So they want us to sketch the solution curve for 1,000 and 250. So 1,000 would be up here somewhere. They have all negative slopes, and it's flattening off at 800, so it should look something like that. For the 250, if 200 is there, 250 would be about here, and they have all positive slopes, so it should look kind of like that. And again, the quality of that slope field is not great, which is part of the reason we're doing this question. So we want to show that the limit as t approaches infinity of p of t depends on the initial value. So what's meant by that is, depending on what we start with, that's going to change whether the fish die off, whether the population approaches some value, and so on. Well, below 200, they're all negative slopes, so they're going to die off. So one case we have is if p of 0 is less than 200, then the limit as t approaches infinity of p of t would just equal 0, because they're going to die off. Well, next case we have is if they're exactly 200. If the initial value is exactly 200, well, that's an equilibrium point because it levels off there. So then our limit as t approaches infinity of p of t would just stay at 200. And then the last case, anything above 200, notice it will push to 800. So no matter if you're at 800, above 800, or somewhere between 200 and 800, it will always push it towards 800. So our last case is if p of 0 is greater than 200, then our limit as t approaches infinity of p of t is just 800. Oops, and I guess I just wrote that in the wrong spot. Sorry. That's for part C right there. The B was just sketching the slope field. All right, so for D, we want to show for what values of P it has an inflection point. So inflection point is when the second derivative is equal to 0, and also that it changes signs. The second derivative changes signs. Well, let's take our differential equation that they gave us. And let's take its derivative. But before doing that, let's multiply this out a bit. So this would be 0.01. If we multiplied it out, we'd get 800p minus p squared minus 160,000 and we'd have plus 200p. And if we distribute the 0.01, that'll give us 8p minus 0.01p squared minus 1600 plus 2p, or in other words, minus 0.01p squared plus 10p minus 1600. So let's take our second derivative. Now notice we're taking it with respect to time. So we'll have a dp over dt for each of these. So we'll have 0.02p times dp over dt plus 10 dp over dt and then that would just be 0. Pull the dp over dt out, so that's 0.02p plus 10 times dp over dt. Oops, I lost a minus here. So we had minus 0.01 p squared, so this should be a minus here and a minus there. Sorry about that. But we know what dp over dt is, so let's replace it. From the original question, we know that that is 0.01 times p minus 200 times 800 minus p. And what's nice about this is already in a factored form. So setting it equal to 0 becomes a lot easier. So we got minus 0.02p plus 10 equals 0. If we add the 0.02p over and divide by 0.02, so that's really 0.02 is 2 over 100 or 1 over 50. So if you do a keep change flip with 1 over 50, we'll get 500 for p. Here, if we do p minus 200 equals 0, we'll get p equals 200. And 800 minus p equals 0, we'll get p equals 800. So we're going to put those on our number line. Remember, p had to be greater than 0. We got 200, we got 500, we've got 800. So if you had, say, 100, 100 is going to make that first parenthesis. Remember, negative 0.02 is like negative 2 over 100. So if you put 100 in, you'll get negative 2 plus 10, so that's a plus. In the p minus 200, you'll get a minus. 100 minus 200, and 800 minus p, you'll get a plus. So we'll end up with a positive times a negative times a positive, so you get a negative. If you do something like 400, again, remember that's negative 0.02 is negative 2 over 100. So if you do 400, that's going to be negative 8 plus 10. So you will, you'll still get a plus. 400 minus 200 will give you a plus. And 800 minus 400 will give you a plus. So we have a plus here. If we put in 600 now, negative 2 over 100 times 600 is going to be negative 12 plus 10. So that gives us, and I'll put it over here, that gives us a minus. 600 minus 200 is 400, that's plus. 800 minus 600, that's a plus. So a negative, positive, positive will give us a negative. And then if you do something like 1,000, these will still be minus and plus, but 800 minus 1,000 will be a minus, so we're back to plus. Now we do have to make sure we label our number line. And these are p's here. Well, we've got 3 spots where our second derivative is switching signs, but keep in mind, when we sketched our potential solutions in the slope field, 200 and 800 were equilibrium points. So there wasn't any continuous graph there, so those can't be inflection points. So our only possible inflection point is this one here. So we'll say point of inflection at p equals 500, since d2p over dt squared switches signs. And the meaning, the point of inflection is your maximum or minimum of the rate. Well, we were increasing, so it is when our rate is the greatest. So the rate of change is the greatest. So the meaning is the population when the rate of change is greatest. Another way to think of it is when that slope is the steepest in the original function. All right, for your homework, you've got to go back and do questions 1 and 2. Feel free to come to office hours today if you had questions as you are working through those. Have a great rest of your day.